In this segment, we will be taking up a problem from kinematics, and we will solve this problem using NT-coordinate system. The reason why we are using NT-coordinate system, I'll discuss in a moment. Hmm, okay, the problem goes like this. There is a plane which is flying at a constant altitude at a speed of 200 kilometers per hour, and then this speed of 200 kilometer per hour is constant, and it's not changing its speed, and then the angle which the heading makes with the x-axis is beta, which is 30 degree, and this heading angle is changing at a rate of minus 5 degrees per second, and we are supposed to find out the radius of curvature of the path at that particular instant. In fact, this question itself, the requirement of figuring out the radius of curvature, should tell us that we should be thinking about the NT-coordinate system. And because we know the acceleration form in the NT-coordinate system to be like this, say d square s over dt square, and that goes with the tangential unit vector plus ds over dt, the speed at which the plane is moving, it's squared over r e n. Now, because the presence of this r, the radius of curvature here, should tell us that we will be using this. And one more thing, that this is nothing but the time derivative of the velocity vector, that is the speed at which, or else I'll just write as, the magnitude of the velocity times et, right? Now, so this is what we have figured out. So now, one more point to be observed is that this portion is known to be 0 for us. That means we can simplify this equation to write as, say, A is nothing but d over dt over of magnitude of the velocity, that is the speed, et times is equal to ds over dt squared over r e n. Okay, now because we know et as a function of time, we will see why I'm saying this. Before that, we can actually simplify this by replacing this with this is nothing but v mod squared over r e n. And we know, because we know beta and beta dot, we can actually calculate et and en and their time derivatives. Let's try to write them. Now, what is et? Et is cosine of the angle beta in I direction plus sine of beta in the j direction. Okay, and similarly en will be sine of beta in the I direction minus cosine of beta, cosine of beta in the j direction. Okay, now these equations, if you see, they are valid for all at this particular instant, and we can actually, if we consider beta to be a function of time, explicitly, if I want to write it here just to make it clear that these betas are functions of time, okay, and that's why we can differentiate them to get the time rate of change of et and en as such. Okay, I'll just remove them for I just wanted to show it explicitly. Yeah, sorry. Now, what is time rate of change of et? Let me write that. So sorry, et dot will be minus sine beta and beta dot. So this is this term in the I direction plus cosine beta beta dot in the j direction, and that's what we need. We don't require the time derivative of en. Now, using this expression here, or if I write equation 1, we can use equation 1 to just equate this like here. Yeah, so et dot is equal to speed over r en implies, so I'll put the values of beta here, beta to be 30 degrees, and beta dot is negative uh, 5 degrees per second, but we have to put in radians. Okay, so so this is negative of 0.5, so this is sine beta, and beta dot is say minus 5 over 360 times 2 pi. So this is beta dot in the I direction, plus 0.866 times minus 5 over 360 into 2 pi j. Okay, now this is equal to en, which is again so 200 over r. 200 is the speed at which it is moving, times the and we have to actually convert it's kilometer per hour to meter per second. So because if we want to calculate in meters, otherwise 200 is fine, kilometers, and but the meter per second we have to change, because this beta dot is in radians per second, so we will divide by 1 by 3600. Yeah, so here also in the same time we can multiply by 1000 just to get the answer in meters per second, in meters, times 0.5 I minus 0.866 j. Okay, now just by solving this equation for r, we should be able to get r to be 637 meters. Okay, so that's how we should think when the radius of curve, anything related to radius of curvature is asked. So that's we should think about the nt coordinate system. Okay, so that's about this question. So we will see you in the next segment with another problem.